In order to use the Laplace transform to solve differential equations, we're going to need to look at what the transform does to derivatives. And what it does is sort of simple. Let's let f and f prime be piecewise continuous. Functions on the interval from 0 to infinity. And assume that the Laplace transform of f exists. In the book they say f is of exponential order. So that is the integral that defines the Laplace transform converges if f grows no faster than an exponential function. Then the Laplace transform of the derivative of f is s times the Laplace transform of f minus f of 0. To prove this, well, this proof assumes that f is continuous. Now, according to the book, the proof can be modified so that it works for f piecewise continuous also, but just to keep things simple, we'll do the continuous version. So we have the Laplace transform of f prime, by definition, is the integral from 0 to infinity of e to the minus st times f prime of t dt. Now let's use integration by parts on this integral here. So let's let e to the negative st be u, f prime of t dt be dv. Then v is going to be f of t, and du is going to be negative s e to the negative st. So we have, so this is uv e to the negative st f of t, which I think I'm going to write as f of t over e to the st, because that's e to the s. Dividing by e to the st is the same as multiplying by e to the negative st. So that evaluated from 0 to infinity minus the integral from 0 to infinity of v du. So f of t times this, we're integrating over t, so s is a constant. So I'm going to take the minus s on the outside and make it minus negative s is plus s e to the negative st f of t dt. Alright, this integral is the definition of Laplace transform of f. So the second term right away is s times Laplace transform of f. So that's part of what we're claiming. And then let's look at the first term. So this is the limit as b goes to infinity of f of b over e to the sb minus what we get when we plug in 0, f of 0 over e to the 0. And as b goes to infinity, this denominator grows very quickly. The numerator grows also, but since we're assuming that Laplace transform of f exists, that is, the f grows no faster than an exponential function, then as b goes to infinity, this fraction is going to go to 0. And that leaves us with f of 0 over 1, which is just negative f of 0. So what we have is s Laplace transform of f minus f of 0, which is exactly what we're claiming. Alright, so let's use this formula and do some examples and make sure that it's consistent with what we know about the Laplace transform. I'll write the formula up here so we can look at it. Laplace transform of f inverse, f prime equals Laplace transform of f times Laplace transform of f minus f of 0. So for example, we know the Laplace transform of t to the n equals n factorial over s to the n plus 1. Let's check the Laplace transform of the derivative of t to the n in two ways. So the derivative is easy enough to take. L of n t to the n minus 1 equals, this is linear so we can take out the n, L of t to the n minus 1, and when we have the Laplace transform of t to a power, we take the power factorial over s to 1 greater power. N times n minus 1 factorial is n factorial, so we get n factorial over s to the n. So here's the first way. Now let's use the derivative rule. If we want to take the Laplace transform of the derivative of t to the n, it should be s times the Laplace transform of t to the n minus 0 to the n. So that's s, Laplace transform of t to the n is n factorial over s to the n plus 1 minus 0. And if we have s in the numerator and s to the n plus 1 in the denominator, we can cancel 1s to get n factorial over s to the n. So that checks out. Let's do this with another function we know. So for example, we know that the Laplace transform of e to the at is 1 over s minus a. So let's check Laplace transform of the derivative of this in two ways. Well, the derivative is easy enough to take. So we have Laplace transform of the derivative of e to the at is a e to the at. A is a constant, so we can take it out. A times L of e to the at. L of e to the at is 1 over s minus a. So we have a over s minus a. And then if we use the derivative rule, L of the derivative of e to the at equals s times L of e to the at minus e to the a times 0, which is Laplace transform e to the at is 1 over s minus a. S times that is s over s minus a. Minus e to the 0 is 1. Let me write that as s minus a over s minus a. So in the numerator we have s minus s, which cancels, and then minus minus a, which is positive a over s minus a. So that checks out. Let's do this with another example we know. So we know that the Laplace transform of cosine of bt is s over s squared plus b squared. And the Laplace transform of sine of bt is b over s squared plus b squared. So what's the Laplace transform of the derivative of sine of bt? So one way to do this is, well, that's easy enough to take the derivative of. The derivative is b cosine bt b is a constant, we can take it out, so it's b times Laplace transform of cosine of bt, which we have right here. So it's b s over s squared plus b squared. And then if we use the derivative rule, Laplace transform of the derivative of sine of bt is s times Laplace transform of sine of bt minus sine of 0 so s times Laplace transform of sine is b over s squared plus b squared minus 0, so this is it. And of course SB and BS are the same thing, so we get the same answer. Now there are formulas for Laplace transform of second derivative and Laplace transform of third derivative too. And we're going to need them. So let's look at those. Well, second derivative is just derivative of the first derivative. So that should be easy. Laplace transform of the second derivative is Laplace transform of the derivative of the first derivative, which is Laplace transform of the first derivative times s minus that function evaluated at 0. Now we have a formula for Laplace transform of first derivative, so it's s times whatever that function says, s times Laplace transform of f minus f of 0 minus f prime of 0. So we get s squared Laplace transform of f minus s times f of 0 minus f prime of 0. So we've got three terms. S squared Laplace transform of f minus s f of 0 minus f prime of 0. Also, we want to take the Laplace transform of f triple prime. That's Laplace transform of the derivative of f double prime, which is s times Laplace transform of f double prime minus f double prime evaluated at 0. Now we just computed a formula for Laplace transform of f double prime. So this is s times our formula says s squared Laplace transform of f minus s f of 0 minus f prime of 0. That was all Laplace transform of f double prime, and then we have to subtract f double prime of 0. So we have s cubed Laplace transform of f minus s squared f of 0 minus s f prime of 0 minus f double prime of 0. Alright, so it looks like we have a pattern here. It looks like if we take the Laplace transform of the nth derivative, then we get s to the n times Laplace transform of f. And then we keep taking smaller powers of s and subtracting evaluations of f and its derivatives at 0. So minus s to the n minus 1 f of 0 minus s to the n minus 2 f prime of 0, etc. minus s f, let's see, for third derivative we're going to go up to second derivative. So for nth derivative we're going to go up to n minus first derivative. S is going to be next to the n minus second derivative, and then minus the n minus first derivative evaluated at 0. So it's sort of easy to see why this is true. The formula holds for the first derivative. That's the first thing we proved. So let's assume that it also holds for the second up to n minus first derivatives. And consider the nth derivative. So I'm proving this by induction. So the Laplace transform of the nth derivative equals Laplace transform of, well, the nth derivative is just the derivative of the n minus first derivative. And we're assuming that the formula holds for the n minus first derivative. So temporarily treating f, the n minus first derivative, as just a function, we can use our original formula to say that this is s times L of the n minus first derivative minus n minus first derivative evaluated at 0. And now, assuming that we know the formula for this, so assuming that the proposition holds for up to the n minus first derivative, we have s to the n minus 1 L of f minus 1 less power s to the n minus 2 f of 0 minus s to the n minus 3, that is, oops, that's actually a power. F prime, etc. So we'll be going all the way down to the derivative that's one smaller than this. So we'll be going down to the n minus second derivative. So that means the second to last term is n minus third derivative, and then the last term is n minus second derivative. So that's all this minus f n minus first derivative evaluated at 0. And that equals s to the n, Laplace transform of f, minus s to the n minus 1, f of 0, minus s to the n minus 2, f prime of 0, minus s squared minus s, so the s is going to go next to, just single s is going to be next to f to the n minus second derivative of f, which is what we want. And then the parentheses end here, so there's not going to be an s multiplying f n minus first derivative, so we're just going to get n minus first derivative. So we get exactly the formula we want. Alright, so that's the theory behind how the Laplace transform applies to derivatives. And in the next video, we're going to put that theory into practice.